Okay, everybody, welcome to class. We are going to get started, and we didn't quite finish talking about extrinsic doping last time, so we're going to start off talking about extrinsic doping. We will then talk about, I'm going to do another explanation of where band diagrams come from. I've been getting a lot of questions about that, so I'll try and explain that a little bit more. I'm going to talk about the temperature dependence of the carrier concentration, Hall measurements as a way to measure carrier concentration, and then we're going to dive into some of the basics of semiconductor devices, and if we have time, we'll get into how conduction can possibly occur in ceramics and polymers, which seems unintuitive. And I doubt we'll get to dielectrics, but we might. So let's start with where we left off. Last time we said, okay, an intrinsic semiconductor is one that for the pure material is still a semiconductor, meaning it has a band gap, and it takes some amount of energy to strip away one of these electrons from their bond, right? This thing's tied up in covalent bonding, but if I give it enough energy, it might leave that bond and now become delocalized, as if it was a metal. In a metal, the electrons are sort of, we call it the sea of electrons, right? They're sort of free to float around and go where they will. That's kind of what's happened to this electron, because it's gone from a bound state here to an empty state, where there's a bunch of empty seats so it can hop around from atom to atom, no problem, because it's up at a higher energy level, okay? At the same time, this lack of an electron, which we call a hole, is also able to move, right? That thing could move if in an electric field, the electron, so the electric field is drawn up there in pink, the electron's going to move towards the positive end of the electric field. Well, the hole is positively charged, so it's going to move the other direction. So the electron goes this way, and the missing electron goes that way, right? The hole for the electron. And that could hop just like diffusion, right? This hole could move over there, and now this would be occupied by an electron, right? Now you've got a missing electron in that spot. So these things can hop just like atoms hopping with the vacancy diffusion mechanism, okay? Any questions on this so far? Yeah, Pramit? Or Fars? Yeah, the hole, I mean, the hole's a weird concept. It's where an electron isn't, and the spot where an electron isn't can move by the electrons moving, right? This electron that was there moved here, so now the spot where the electron isn't moved from there to there. We treat it like a quantity, and what's really weird is that it doesn't have the same mobility as the electron, right? What was mobility? Mobility was kind of like the friction, right? We said that's like the drag force. If I jump out of an airplane, the coefficient of friction of my body against the air, we could quantify that. And the analogy for electronics is what we call the mobility. It's essentially like the drag force that it feels in response to an accelerating force, right? The electric field which causes it to accelerate. It experiences a drag. And what's interesting is that this free electron moves, but it experiences a different drag than the hole. Is that weird? It's a little weird. It's the truth, okay? So because of that, the overall electrical conductivity, this term right here, the electrical conductivity is now going to have two components to it in an intrinsic semiconductor. It's going to have contributions from your N, that's the number of electrons, right? P is the number of holes. In an intrinsic semiconductor, every time that you get an electron, you create a hole. So N and P are equal to one another in an intrinsic semiconductor, right? N and P are the same number, and we just call that the intrinsic carrier concentration, N sub I, okay? Does that make sense why that is the case? To create an empty seat, you had to pick a person up, right? So your electron created an empty seat. You've got equal numbers. But what is not the same, first off, they have the same charge. It's the absolute value of the charge of an electron, so those are the same. Absolute value of E is the same in both of these. What is different is their mobility. The mobility of an electron is not necessarily the same as the mobility of a hole. They can be very different. In fact, they are almost always very different numbers, okay? But the overall conductivity of your sample is going to come from the movement of these electrons and the movement of the holes. You can't neglect one, right? The overall net current is defined as the opposite direction of electron flow. So the current is going that way, the same direction as your holes. But that's happening because electrons are going that way. They both contribute to current, electrical current. Any questions? Yeah.
So isn't that the mobility of the whole
It's more complicated. If you take a class in solid state physics, so physics describing condensed state matter, they get into it in more detail. But maybe think of it this way. Let's go back to our double-decker bus analogy really quickly. Right? If we have a double-decker bus, we're in jolly old England, and you've got the valence band is filled up with people occupying seats, and if somebody pays the energy price, they can climb up the ladder to the upper deck where there's a bunch of empty seats, right? These things are all empty, just waiting to be filled by people. And so if a person does that, if they move up there and they now sit here, there's still going to be a difference between the ability for people to shuffle from empty seats to seats where there's one that's filled, right? So this person can move very easily on the top row, wherever they want. But this one, it's sort of a one-at-a-time process, and there's an activation energy. Maybe that's the best way to describe why the mobility should be a little bit different, but it is. In this class, you can just take it as a granted that the mobility is different of this empty seat moving around here and the electron moving those empty seats up top, okay? Yeah, Alan?
So you had said that the current goes in the opposite direction of the electron?
By definition, current in an electrical circuit, yeah, go ahead. Yeah, so like in EE, when you learn about circuits, right, and you say that the current travels this way, then that means that the electrons are traveling that way. That's just by definition. Electrical current goes the opposite direction of electrons. I don't know, it's just convention, okay? So, oh, guys, we did it. Now we did it. That's a bummer. That's a stone cold bummer. All right, give me 1 second while I fix this. While I erase so many dots. All right, you guys realize that every one of these bonds has electrons in it, right? I'm not going to draw all the electrons, but it's assumed you realize that each one of these things has electrons. What I will draw is phosphorus's extra electron, right? Phosphorus is not a group 4 element, it's a group 5 element. It's got 5 valence electrons. It only needs 4 of those to be tied up in bonding. So that 5th one, it doesn't really need to have it to satisfy its octet rule, which is like they want to add up to 8, right? It wants to look like a noble gas. Right now, it looks like a noble gas plus an electron. So it doesn't really want it very badly. It still takes energy to pull it away. Phosphorus has, if we look up its periodic table, if we look at the periodic table and we look for phosphorus, it has 15 is its atomic number. That means it has 15 protons and 15 electrons. So if we take away an electron, it's now no longer balanced. So that does cost energy. It just doesn't cost very much energy. It's like if I walked up to Alan and I'm like, hey, Alan, do you have $100? And he's like, no, I'm not giving you $100. But if I'm like, do you have a quarter? And if he's got it, he's like, yeah, I guess, right? You don't care about it. That's kind of what's happening here. It doesn't care about that other electron. It's still bonded to it technically. It's just not a very strong bond, right? And since it's not a strong bond, what can we do to it? We can ionize it, meaning we can take it away. We can make phosphorus an ion. We can turn this into a hole, right, by pulling this thing away and now making a delocalized electron, okay? The hole is now positively charged, right? Because that phosphorus atom, we took an electron away. Now that dopant is positively charged, right? So charge neutrality is still maintained. We've got this negative charge floating around through here. We created a positive charge. Everybody with me? So in this case, the electron is vastly more mobile than the phosphorus atom. Phosphorus atom, it could diffuse, but it has to replace other atoms. That's going to be way slower. Diffusion of mass is way, way slower than the electron, which is occupying that top level of the double-decker bus. It can move around really easily. You guys follow me? What does this look like in terms of an energy diagram? It looks like this. We've got our valence band down here. And if it was pure silicon, then this is completely filled. The Fermi level somewhere in the middle. Fermi level is, remember, at 0 Kelvin. That's the electrons would fill up to some point, and it's somewhere in the middle, so they fill up to here, and that thing is totally empty. For an intrinsic semiconductor, the way that we get conduction is by promoting things across this big energy penalty to sit up here. That's not what happens in extrinsic semiconductors. Instead, it looks like this. Was it a big energy penalty or a small energy penalty that we paid? It's a small one. We paid a small energy penalty. So where do we need to draw it in our diagram? We need to introduce something. We need to introduce a state in the band. I'm going to draw it right here. This represents the phosphorus atom. It's an individual dopant, so we can put an individual state in that band. And to pull that electron away and put it up in the conduction band doesn't take very much energy. This thing can be promoted up to here pretty easily. And when it does so, we had a state here, and now it's an empty state. You guys with me? So we cheated. We found a clever way across this big band gap. We put something in the material that puts a state in an otherwise forbidden region. Pure silicon, you can't put anything here. Silicon doped with phosphorus, you start putting states in that gap. Jaden?
So that makes it really quickly a lot more conductive?
Yeah, so the benefit to this is that you don't require really high temperatures to ionize that electron. Remember, ionize means that you're stripping it away from the phosphorus atom donor. This thing can become ionized, meaning it's now a free electron, free to move through the silicon lattice as an electron. You can do that at low energies. That's one benefit. It doesn't require high temperatures. What's the other benefit here? What do you think? Well, we have already said that this phosphorus atom is not mobile, at least nowhere close, like 1 billion times worse in terms of mobility than the free electron. Phosphorus atoms can technically diffuse, but it's going to be way, way, way slower than the electron. So is the number of holes now equal to the number of electrons? Yes, technically. But is the mobility even close? Not even close. So we're going to modify our term up here. This relationship for an intrinsic semiconductor, we're not putting any holes in the valence band. Instead, we're putting them on an individual phosphorus atom, which is not mobile at all. So this term just disappears. All of a sudden, we have a material that conducts just electrons. We've gotten rid of the holes, and that's important for reasons that we'll get to in a minute. Okay? Yeah?
So does that also, for metals, this equation for conductivity, is it just the first, that first?
So for metals, yeah, you're right. A typical metal like aluminum or copper, the way that we calculate its conductivity would be like just this first term. We'd say they have free electrons, they have some charge, and they have some mobility. We don't think about holes with electrons. This is just a semiconductor concept. Okay, it's a good question. So that's doping it. We call this N-type doping. Why do we call it N-type? Because it produces electrons, and we call those N, right? The concentration, the carrier concentration for electrons is N. That's the variable we use. And P was for holes. You can also P-type dope this. How would you P-type dope it?
Do something from the group to the left. So like
Yeah, we had silicon right here was group 4. Adding something to the right gives it an extra electron. To P-type dope it, we want to give it an extra missing spot for an electron. So something to the left, like boron, aluminum, gallium, indium. Group 3 elements are going to P-type dope it. So in our lattice, they're now going to look like this. If we get rid of one of the silicons, let's do a different color. If we get rid of silicon, and instead we put a boron there, boron only has 3 electrons, so it's not able to fulfill its 4 bonds like it's supposed to. Instead, it has a built-in hole. Like, it can't form the bond like it's supposed to. It's missing the electron, which means that we can ionize boron. It's going to cost a little bit of energy, but if we want, we can take an electron nearby and we can make it sit on that boron site, making boron negatively charged, whereas the phosphorus became positively charged. When it was ionized, the boron becomes negatively charged, and in doing so, we now have, let's say it came from over here. Oops. This electron came and occupied this site, making boron negatively charged, but putting a hole in the silicon lattice. Everybody with me? What does that look like in terms of the band diagram? It still takes a little bit of energy to make this happen, but it's on the other side. It's now down here. this was a hole for a boron atom. For each individual dopant, every boron that we put into the structure, we're putting a little tiny state right there, which is close to the valence band edge, which means if you've got an electron hanging out in the valence band, it can jump up and occupy that level. So now that level becomes occupied like that, and you create a hole in the valence band. And for the exact same reasons that we just described for phosphorus not being mobile, the boron atom is not particularly mobile. It can diffuse, but it's going to be slow, right? Meanwhile, this vacancy, the hole where an electron used to be, is much, much more mobile. You guys with me? So instead of our term being, so in n-type electrons, we could basically cut out that term because the phosphorus atom is such a slow diffuser that we just don't include it. This is the opposite. We're going to be able to cut out that term, and it's only P, it's only holes that are moving in the material. So this is really important because, like the device I showed you last class, the thermoelectric device, the only reason that works is because we can make the little tiny metal legs that were standing up between the plates, those things have to be alternating n-type, p-type, n-type, p-type. It has to be holes, electrons, and I'll show you why in just a moment. Any questions on extrinsic doping? On how I got this diagram, this band diagram over here? Yeah, Jaden?
I was just going to ask you to briefly define intrinsic and extrinsic.
Intrinsic means we didn't dope it. It's the pure semiconductor. Extrinsic means you're intentionally adding impurity atoms of some sort to either be electron acceptors. The boron accepts an electron, and in doing so, it creates holes, or to be an electron donor, like the phosphorus gave away an electron to become an electron donor. Everybody with me? These things are ionized, so it did cost energy for these things to basically, to create the carriers which become mobile, it did cost a little bit of energy, but it's not very much. It's much less than an intrinsic, which requires you to jump this whole gap. That's much bigger energy penalty. Okay? Keep going? Let's keep going. So again, we modify our expressions to become basically, it's an assumption, but we basically say the number of carriers in an n-type dopant is so much greater than the number of holes, and really just the holes aren't mobile, that we just leave it off. The overall conductivity becomes just the first term. And the same thing for p-type doping. The number of holes is so much greater than the intrinsic number and the number of not mobile boron atoms that we just ignore it. It just becomes that. Okay? Okay, let's keep going. Somebody had a question, where do these band diagrams come from? Let's dive into that a little bit more. If I take an atom, and I'm just going to draw a lone atom, it's got a nucleus, right? And then it's got these electron shells which go around it. And we know if we literally start from the bottom and work our way up, we could write how many electrons live in these shells, right? We'd say, okay, you can put 2 electrons in the 1s, you can put 2 electrons in the 2s, and you can put 6 electrons in the 2p. And we could keep on going. 1, 2, 3, 4, 5, 6. Okay, you guys with me? So we just did what element? We did 1s2, that gets us to helium, 2s2 gets us to beryllium, 2p6, it got us to neon. So this would be the element neon, right? And if it's a lone atom, then the difference in energy between these energy levels are discrete numbers. We would say that this right here, between those two things, is a discrete number. So what you'll often see in Gen Chem is this drawing. In terms of energy, we just draw discrete lines. We say this is the 1s, that's the 2s, that's the 2p. We can put 2 electrons, 2 electrons, 2, 2, 2 gives us 6 electrons here, right? What happens is as you take another atom and you put it nearby this thing, these orbitals start to overlap with one another. If the orbitals overlap with one another, we cannot have electrons occupying the same volume of space at the same energy. So the cheat that happened quantum mechanically to make this not violate Pauli exclusion principle is instead of them occurring at discrete energy levels, these discrete energy levels start to smear out a little bit and happen at different bands. Okay? And you can see that if you were to calculate what's called the density of states. In this drawing here, this graph, this shows you the density of states. That's the states where you can put electrons. So going from low energies over here, negative, relative to the Fermi level. The Fermi level means if you absolute zero, you could fill electrons up to that point. Okay? These are these same things that I just drew you here, except I drew them really simplistically, and in a real material, they're anything but simple, right? This is a material Mx, so it's an anion and a cation. The cation is M, the anion would be X, right? And here you see in different colors, sp and spd, right? So these are like the s electrons for the M cation right here. Or sorry, these are the d. How do you know that they're d? Because d has 5 orbitals, and these can occupy, there's lots of volume under this red curve. Whereas the s can only put 2 electrons in the s, so they're a lot smaller. Like the green is small. Where's the other one? The yellow is small. You can't put as many electrons in them. There's not as much area under the curve. You guys with me? So this is just an overly simple picture of what happens in real structures. In real structures, it's complicated. And to make it more complicated, these like the overall sum of your available states can drop to 0. And this is the band gap. You have no available places to put electrons over some space and energy. And then you start to have it again. So if your Fermi level happens to land right in the middle here, you have a semiconductor or an insulator, depending on the size of this gap. This gap's given in electron volts. That's about a 1 eV gap. That's just like silicon. That would be an intrinsic semiconductor, right? If this was, let's say that this 0 point was shifted over and it was right here, you would have a metal because you have a partially filled band. It would be a metal. If it was up here, you would have a partially filled band. If it was right here at the edge of this, it's still a semiconductor, right? It's just it's a very small band gap one. Yeah.
It looks like there's several band gaps on that graph.
Yeah, there can be more than one.
Okay.
Yep.
We're not getting into that.
The one that we care about is the one near the Fermi level. This one also exists. It's just not very relevant to our properties. Because, again, this is where electrons live, is down here. They would have to get excited way up to there. That can happen, especially if you hit it with something high energy like a laser. You can excite things to high energy levels, like really high energy levels. This is much lower. It would rather be here, or actually back down here. But yeah, you can get it up here. That happens. Everybody with me? So the point is, the picture that we draw in chemistry, first off, this picture is just only works for individual atoms. And even then, it's overly simplistic because I'm drawing everything as circles, and bonds have non-circular shapes. But it's a starting point. So a little bit better picture is to think about things in terms of energy like this, but this doesn't work for anything other than a single atom because they start to overlap, and that leads to bands. And for real materials, it looks like this. Okay? Everybody with me? Okay. Any questions I can answer? Let's keep going. Okay. What should the temperature dependence do for our carriers? If it's an intrinsic semiconductor, intrinsic means that all of our carriers have to jump this big gap, right? If we want more carriers, we have to get more and more of them jumping from here up to there. Meaning if you heat this thing up, as long as you keep on heating it up, you should get more and more carriers that are able to jump that gap. So the number of carriers should always increase. And that's what we see. Plotted here is our carrier concentration, N sub I. That's the intrinsic carrier concentration. It increases as you heat this thing up. And these things, it sort of starts to slow down, but they keep on increasing. So this material, 10 to the negative 30, that is not a very good conductor. But 10 to the positive 10, that's a really good conductor. Silicon carbide starts to become a better and better conductor as you move to higher and higher temperatures. And all semiconductors do. Okay? Any questions? Now, if we plotted this in a different way, as we love to do in material science, if you plotted this as the log axis over here and then 1 over temperature over here, those lines which were not linear become linear, right? The reason that they become linear is because this is a thermally activated process, just like we've seen 10 different times in this class. The number of carriers can be described as some constant out front, n, multiplied by the exponential of a activation energy, and this time that is just the band gap. The activation energy is the band gap, divided by, this time, 2 kT. Where's the 2 come from? I can't remember. It's there. Okay? I can look it up if you want. What's nice about this is that then if you were able to determine carrier concentration and there's a measurement to do that, and do that as a function of temperature, you'd get these nice linear curves. From the slope of these curves, you could get your band gap, right? The slope of this curve should be band gap divided by 2K. That's KB, Boltzmann constant. Everybody with me? Okay. All right, how about this? Clicker question. The question is as follows. We're now talking about an extrinsic semiconductor, not an intrinsic one. It says an extrinsic semiconductor will increase in electrical conductivity with increasing temperature over all temperatures. Meaning you start out at low temperatures, 0 Kelvin if you want. As you start to heat it up, it should become a better and better electrical conductor over all temperatures. True or false? Question? What's that?
Semiconductor melt, they get
Oh, that's a good, we're considering when it's a solid. So good question. We're talking about the range of temperatures where it's still a solid. So when it melts, we're not talking about that temperature range. When it's a solid, if I keep heating it up, should it conduct more and more electricity proportionally, or just keep increasing with temperature? Question, Lana?
Are we looking specifically at a p-doped or an n-doped?
It says an extrinsic semiconductor, so this should work for either, the answer to this question. So get your answer in. We're going to close the poll. This one, I think I give credit either way because it's tricky. So I think this is just participation, but get your answers in. Okay, I'm going to close the poll. Okay, the answer is technically true, but it looks like it's false, and I'll show you what I mean. So you should have gotten credit no matter what by answering something here. Here's what happens. For an extrinsic semiconductor, this is the electron density, so the carrier concentration of electrons. This is the intrinsic semiconductor line over here. As you heat it up, it just gets better and better because it's got more and more carriers jumping the gap. But think what happens with an extrinsic semiconductor. It has something that doesn't require very much energy, and there's a finite number of them. So we'll do this one, right? There's a finite number of these phosphorus atoms, right? You all agree? We dope it to have some number per volume. So there's a fixed amount. And this is a small energy. So we could imagine a temperature at which basically all of these are ionized, but we still don't have enough temperature for these things to start ionizing because it's a much bigger gap. You agree? So because of that, you see 3 typical regimes or regions for extrinsic doping. You see the freeze-out region. We call this region down here freeze-out. Your carrier concentration plummets to basically 0 because you don't have enough thermal energy even to ionize that little bit of energy you need. That'd be like if Alan is so broke, if his level of broken out is in the freeze-out region, I'm like, give me a buck. He's like, I can't do it. That's freeze-out, right? But most people aren't in that region. It just takes a little bit of thermal energy, and you're in the extrinsic region. This is your extrinsic region, where depending on what level you're doped at, these represent 5 different dopant levels. This is a little, more, a lot, right? You go from, whatever. As you move this way, actually that's a little bit non-intuitive. You got to look here. In the intrinsic material, it's doped with 1 e to the 17th, so it intrinsically has some carrier concentration. Okay? So here they're showing you that the number of acceptors is less than the number of donors, but as you increase the number of acceptors, it's approaching more and more extrinsic scenario. In other words, as the number of carriers become equal, it's collapsing towards the intrinsic scenario. But as you give it more and more of one type of dopant, it's becoming more and more extrinsic. In either case, this region looks flat, right? It looks flat because we're on a log plot, and this thing is technically, the intrinsic is technically still increasing. right? If we were to extend this graph out, this thing is technically still increasing, but it's tiny. The observed conductivity doesn't look like it's changing in this region. It technically is. It's just really a slow increase over that region. And then, once you heat it up enough, all of a sudden you start kicking in your intrinsic contribution. So you doped it. You doped this thing so that you could get phosphorus ions ionized. But if you keep on heating up this extrinsic semiconductor, eventually you're going to get lots of these guys jumping up, and your P and N concentrations are going to vastly outnumber your extrinsic dopants. And so it starts to look like an intrinsic material. At high temperatures, it looks like P and N are the same number again, because these are orders of magnitude higher than what you doped it to be. Everybody with me? Can I answer any questions? This is a pretty cool, yeah, question?
Yeah, so when you're looking at like phosphorus and it has that empty site, is it easier for like an electron from a silicon to fill the phosphorus site or just to jump the whole?
Oh, technically it would be easier for it to fill the phosphorus site and become ionized. And thereby putting a hole in this band. Yeah, that can happen. But it's still, think of what the energy cost is. It's still big. It's a pretty big jump to go from here to here. And there's a relatively small number of those. But yeah, you're right. Other questions I can answer? Yeah.
So did you say as the number of atoms or the concentration of atoms you dope it with becomes equal to the concentration in the lattice, it just becomes intrinsic?
So the trick here is take a look at this. They show that the intrinsic carrier concentration is 10 to the 17th. And here they're showing different amounts of acceptor ions. An acceptor ion, right, a dopant that's an acceptor is something like boron. That accepts an electron, right? It makes it p-type. As you increase the amount of these boron from a number well below 10 to the 17th to a number that's even less, even fewer acceptors, then your number of acceptors becomes much, much less than the number of your donors intrinsically. So it becomes an extrinsic material. You've doped it N-type in this case. Okay? Other questions I can answer? And again, this is important because we want to build devices that either conduct electrons or holes. Why? Why do we care about that, right? So let me show you from the example of the thermoelectric from last class, right? So if we go to my web page, and we go to research, and we go to how thermoelectrics work, here's the basic idea. A thermoelectric device consists of, at its heart, N and P-type components, right? So you have, let's imagine it in power generation mode for a minute. In power generation mode, we're going to harvest an electrical current by an existing temperature gradient, right? One side's hot, one side's cold. You have carriers in your P and your N-type semiconductors. In your N-type material, you have electrons. You have at least many more electrons than you have holes. In your P-type material, you have many more holes than you do electrons, okay? If you have a hot side and a cold side, these things will move from the hot side to the cold side. I'll show you why in just a moment. But as they do so, look what happens. As they both move down, you have electrons going that way. The absence of electrons going that way, you have an electric current in your material. If this was both N-type and N-type, you would not get any current. You'd have just as much current going that way as that way. You'd have no net current. So you have to have both types of materials for this to work. Okay? So why do they move from one side to the other? We have to consider a bunch of band diagrams. So here's a P-type material. Notice I've drawn this dotted line for our P-type material. These represent like the donors that you can jump up and you can fill the spot because you've put acceptor ions there. Excuse me, acceptors, not donors. Here in the N-type, you put donors like phosphorus that can easily ionize. So this Fermi level, represented by this dotted line, when you put this material together, literally you press it together, under equilibrium, this dotted line has to become equal everywhere. And the only way to make it equal everywhere is to get what's called band bending happening. For this dashed line to be constant throughout the material device, these bands have to bend a little bit in funky ways at those interfaces, okay? So that's happening. And now we put a temperature gradient across this thing, and what happens? Well, we know in a hot side, the number of electrons that can occupy a higher energy level becomes more. than that on the cold side. Fewer of these can occupy these higher energy levels on the cold side. So if we take our device and we make it hot in the middle, cold on the sides, which is just exactly what's happening if you think of this thing in one dimension, going from metal, P, metal, N, metal. That's exactly what I've drawn here. I've just put it together in one direction. You start out with metal, P, metal, N, metal, right? When you put a temperature gradient across this, you have more carriers next to the hot side, more carriers next to the hot side. These are electrons. These are holes. So if there's more on this side than over here, then there's a concentration gradient. And they're going to move from here to here. And these are going to move from there to there. So what you see is there builds up a voltage difference, right? As these things move over, you have separation of charge over some distance. That's a voltage. All of a sudden, you created a tiny little battery. By putting together an N, so a metal, P, metal, N, metal, and putting a temperature gradient across it, you produce a voltage, a difference in charge across some difference, right? In terms of difference of space. So to make these things work better, there's lots of things that you would change, but that's the main idea behind it. And you could not get these things to function without P-type and N-type materials. Everybody with me? If you don't understand this perfectly, that's okay. I'm just trying to get some main ideas home that why these things might matter. Jaden?
Why couldn't you do it with just one P-type or one N-type? Because like they're both creating a potential difference in voltage.
So you have to have a circuit. These devices have to exist as circuits. So if you just had one of them, which side would be hot? Right? If you, let's say we get rid of the N, and we just take metal and we connect it down to here, we skip this thing, the problem is you'd have an imbalanced charge. You wouldn't have charge balance. So I'm not going to get into it because this class isn't about devices per se, just the main idea I wanted to get home. If you are interested in these devices, there's a great course you can take called Electronic Properties of Solids in our department, where you learn a heck of a lot. There's a bunch in electrical engineering and physics as well. Why else do we care about these things? I'll show you some other devices in just a minute, but let me say a few words about mobility. Mobility represents like the friction that these things have as they move through the material, and that depends on lots of things. Temperature, for example. We get the example of me trying to take a tennis ball and roll it up the middle of this section. If you're at a higher temperature, your feet are moving a lot more. The odds of you kicking that ball and scattering it go up. So we know that temperature is going to kill our mobility, but other things will too. Here they're showing mobility. Sorry, the tiny scale bar on that. That is mobility versus carrier concentration, N. The more and more dopants that you put in a material, as you dope it 10 to the 15th, 18th, 20th, whatever those are, your mobility starts to fall to some minimum value. Why should dopants influence it? Well, think about it. What are dopants? Dopants are nothing more than this. The more and more boron ions I put in this lattice, if you have a hole that's traveling through this thing, remember the hole is positively charged, it sees its old friend the boron, which is now negatively charged. It might temporarily recombine with that, or at least be distracted, right, by it. So the more and more of these that you have, even though they increase your carrier concentration, they reduce your mobility. So what's the net impact on your conductivity? Conductivity depends on both of those things, right? Your carrier concentration and your mobility. Typically speaking, you can increase your carrier concentration by many orders of magnitude by doping, and your mobility only decreases by 1 or 2 orders of magnitude, right? If we look at it right here, your mobility goes from 1,500 down to 500. That's 1 order of magnitude, basically. So it gets worse, but it's worth it because you get so many more carriers, okay? Can I answer any questions? And we've already talked about temperature. There's this initial, we're going to ignore this lower region. Most of the time, it makes sense to think that your mobility goes down with higher temperature. What's happening down here is harder to explain, and we're not going to cover it in this class. How do you measure how many carriers you have in your material? That might be important, right? It's going to tell you your conductivity. You can get your mobility from that measurement. It's tricky. You can't just like open your material up and count electrons. So you have to get creative in how you do this. And a clever person came up with how they do it. It's called a Hall measurement. Here's how it works. You take your sample, and at its most basic, you're just going to pass a current through your sample. You hook a battery up to it. So again, you've got current going that way, which means your electrons are moving towards the positive end of your battery, right? So electrons are going that way if current is going that way. And then what you do to make it a clever measurement is you put a magnetic field across this thing, transverse to the direction of the current. So electrons are moving that way through your sample. If you put either a magnetic field, have they shown it here? Yeah, B, Z, a magnetic field going up, like up in that direction of the sample, then you have a charged particle, your electron, moving through a magnetic field. What's going to happen to it? Lorentz force, right? You took physics. Charged particles get bent by electric fields. When they move in an electric field, they get diverted. They experience a Lorentz force. So you take the direction of your current, which is that way, and you take the direction of your magnetic field, which is up, and then your third finger from the right-hand rule tells you that the electron's going to move that way, right? So you'll literally see if you take a multimeter, something that can measure voltage, and you put it here and here on your sample, you have a battery here causing a current to go through your sample. You have a magnetic field. You will see a voltage right here spontaneously appear. You guys not amazed? This is really clever. This is really clever. So this voltage that you measure is called the Hall voltage. And from the magnitude of that Hall voltage, you can calculate the number of carriers that must have drifted to one side over the other, right? So here's the math for it. The Hall voltage is equal to the Hall coefficient, R sub H, that's this guy right here, R sub H, times the current, times the magnetic field, divided by time. You have to make sure the units work, so they have to be all in the same types of units, SI units, unless you're a barbarian, right? And then this Hall coefficient, RH, is just equal to 1 over your carrier concentration. So all of a sudden, you have a really slick measurement on a small sample that doesn't take much. A simple magnetic field will do this, and it will tell you what's your carrier concentration. You can do this as a function of temperature. You can do all sorts of clever things with these, okay? All right, let's talk about a few other devices. A few other important devices. I think, arguably, the most important thing that we've ever discovered as a species is the p-n junction. The p-n junction. That's a junction between a p-type material and an n-type material. Why is this so important? This makes everything possible from solar panels to transistors, which is all electronics. How do they work? Well, you can think of them, let's start with just a diode, LEDs, right? LEDs are p-n junctions. If you have an alternating current, right, this is your voltage, the voltage is going to produce an alternating current. If I'm switching, I take my iron wire demo from the wall, positive and negative, that's switching because the wall is alternating power. It's switching from 120 to 0 to 120 to 0 each 60 times a second, 60 hertz. If you don't want your current to be jostling back and forth, but instead you want it to go one direction, which we want in so many devices, like this computer runs off of DC power, direct current power, meaning the current goes one direction. But the power, when I recharge it, comes from the wall. So every single one of these devices, right, where are they? All right, I don't have mine, but you all have them. Those little converter boxes for your laptops and phones and everything else, those have a rectifier. You have to go from AC to DC, right? How do you do that? What we'd like is instead of this alternating voltage, we want just one side of it. How do you do that? With a p-n junction. Here's how it works. It's pretty amazing. You grow a material. I've actually got it right here. You grow a material and you make it, let's say that it's initially n-type. So when you grow the silicon, perfect single crystal, you introduce phosphorus in that growth process. So it's a nice, perfectly organized crystal, except that you've replaced some of the silicon with phosphorus. So mostly everywhere, it becomes n-type. You've got an excess of electrons, right? Now what you do is you sandwich that with a material that's p-type. You can either take a separate single crystal and smush them together. That's not what they actually do, though. Instead, they take your material and they just add a bunch of holes. They implant. If you put phosphorus over here, maybe you put a bunch of boron over here. If you put a lot more boron than there was phosphorus, now you've got a p-type region and an n-type region. Think what happens as you now put a voltage across this thing. If I put a voltage across this thing, the way that they've got it drawn, the positive side is over there, so my electrons are going to want to go that way, right? Everybody with me? Well, think what happens. You've got electrons traveling through this friggin' minefield where if they get close to a hole, they're going to just recombine, right? Energetically, that's what they want to do. They want to recombine. What does that look like from an energy standpoint? Well, this is energy on your y-axis. You have all these electrons in your conduction band. As you move them that way, which is moving through the circuit, they're going to fall down and occupy a hole. As they do so, there's a change in energy. We don't delete energy in this class or in this universe. And so you have to give off something with that same energy. You give off light. A rectifier is just an LED. Inside that little box that you have is a bunch of light being created. You don't see it because that's not what we're using them for. But they are creating a bunch of light. This allows current to travel this way. Excuse me. It kills current traveling this way because all these electrons just recombine and give off light. But if you send it the other way, if you switch the polarity, electrons go that way, holes go this way, no problem. They never run into one another. And so you get current. So this allows you to have current in one direction only. You made a rectifying junction, right? A PN junction. Yeah?
Why don't the holes ever get filled up? Is there something creating more holes as it goes? Or?
Why don't they get filled up? So you have to think about this in steady state, meaning not changing with time. And what you'd see is a continuous depletion. As you're moving electrons here, they're ionizing these things, and then they would drift back. Yeah. You can overload it. There exists a voltage that's large enough, or if this thing is really narrow, that you can get some to sneak through. We'll show you that in a minute. That's a transistor. Okay? By the way, this is the exact basis of a photovoltaic, a solar cell. Every single solar cell is just a PN junction. You've got a material which is P-type doped and N-type dope. It's just the exact opposite. In comes sunlight, so instead of light being given off, you have sunlight coming in. It hits one of these things that are in the in-between region. We call this the depletion region, where these things come together. It spontaneously now creates an electron-hole pair. That thing might recombine. You don't want that to happen. Instead, you want these things to drift and separate, and then you collect that current. Okay? Some do recombine, and the more efficient solar cells will prevent the recombination by making this region really small or applying a voltage to pull them away from one another. Right? But this is solar cells. Every single solar cell is just a really simple PN junction. Why else do they matter? Transistors. Right? A transistor, if you've played a guitar, you know that technically while you play your guitar and it's got its little electromagnetic pickups, they're producing a tiny little voltage using piezoelectrics, which we will cover probably Monday, right? It produces a tiny little voltage that is not good for anything. Instead, you take that tiny little voltage and you pass it through something, and you want a small input to become a large output, right? So inside an amplifier, when it actually makes all the noise that you can hear, it has to get enhanced. And you do that with a transistor, right? How does it work? You've got an N-type, a very skinny P-type, and an N-type. You apply, when you take your guitar amplifier, you apply a big voltage between these two things. Okay, there's a big voltage. That's the wall power. And then you have a tiny voltage coming from your guitar. N-type and P-type, if you send a current this way, most of these electrons are going to get combined. The recombinations are going to occur. They're not going to make it through that P-type region. But some of them will. A small fraction of them will make it through because this is thin. You make the P-type region thin. And then they drop down in voltage in a big way. So your signal, the voltage starts out small here. It gets greatly amplified as it makes it through that depletion region because you put a big bias across that one. Okay? Everybody with me? We could go on. Like, pretty much every amazing electronic device at its heart is PN junctions. How about this one, a MOSFET? A MOSFET is what we call a metal oxide semiconductor field effect transistor. It's a mouthful. Here's what it is. It's basically, this is how we store energy, right? You can either store memory like this, or you can make a transistor out of this. Inside of all of your devices, they are filled with MOSFETs. How does it work? You start out with a P-type substrate, so it's all filled with holes. Then you implant a region, and you're going to do this on the homework that I've assigned, where now you have an N-type region by implanting it or diffusing in extra electrons. So you've got holes, electrons, electrons. If you put a voltage, across these two things, you'd like to make your electrons transit from here to there. And in doing so, you can store memory, right? Flash memory works like this. You can either store information as traveling between these or not. But right now, if you move an electron from an N-type region into a P-type region, recombination will occur. No current will get through. But you can cheat. You can make this region temporarily N-type by applying a voltage across between your substrate and the top of your gate. We'll talk about how that works next class.